Yeah,
I'm gonna
you
stand on
talk.
my feet all day at work. It sucks.
Yeah, and you talk about your kneecaps being out of place and stuff. Yeah, that's got to be no fun.
Yeah.
So we could analyze that too, but
I'm,
let's not go there. Okay. Uh, okay. So, uh, okay, let's say we got a pendulum here. Pendulum has a length L, and it's at distance x from its equilibrium position. It's on this side of equilibrium. And it's swinging at velocity we'll call it V, P. I don't want to use P because we're talking about momentum. Okay, we'll just call this velocity V1. Okay? And it's got mass M1. Man, this chalk, we've got to get better chalk. Mass M1. Then we've got another mass that is at the instant before collision, moving at velocity V2. And both of these velocities are in the horizontal direction. Okay, they're going to collide, and then after collision, what will be their velocities? So let's say that this is a picture before collision. Now I promise you not to get too evil with this problem. I could say something like, okay, after the collision, this pendulum swings back to some maximum distance. Okay? Swings back to some maximum distance. What's its velocity after collision, and then what's the velocity of this thing after collision? It would be a perfectly okay problem. You probably wouldn't have too much trouble after we analyze this one. So let's just analyze this one, though, a little simpler, and say that after collision, and of course this thing also has a mass M2. Okay. Now let's keep in mind that this isn't a completely isolated system. You have a tension in the string here, then it's just mgx over L. You have that tension. So in the microsecond after collision, or the time it takes, let's say the collision's very quick, so that we can at least approximate this by saying that the system is effectively isolated for the duration of the collision, and then immediately after the collision, this tension now begins to act and interferes with everything. So this would be after collision. We know the velocity of this thing. Okay, so assume.
is that velocity above the mass M2 supposed to be 1 or 2? Because there's two V1s.
V1 is the velocity here, V2 is the velocity here. And V1 is the velocity of the mass M1, V2 is the velocity of mass M2. Does that answer your question?
Yeah, it just looked like a 1. I couldn't make out the 2.
Well, that 2? Yeah, well, I complained about this chalk, and that was actually a, there we go, is that better?
Yeah.
Okay. Yeah, I can see it now, so. And of course I'm looking at it backwards. If I can see it backwards, it must be okay. Okay, so we assume effectively isolated system for the short duration of the collision. And boy, that C's awful small, so is that O. Okay. And that's important because if the collision takes a significant amount of time, then the tension, the horizontal component of this tension, is going to mess with the velocity of this ball, and it won't just be the Newton's third law interaction between this ball and this ball that's causing the change in momentum. And the changes in momentum then wouldn't be equal and opposite. And in fact, they won't be, but if it's a very short collision, we can neglect any contribution that tension makes to the change in velocity of the first ball. Okay, so you might not understand everything I just said there, but it's going to be out there on YouTube by this evening, and the whole world can have at me for it. Okay, so, not that they will, they'll pay much attention, but okay, so assume effectively an effectively isolated system for the short duration of the collision. That's important to state that. Okay, so let's assume let V1 equal .40 centimeters per second times I. We'll make that negative 40 centimeters per second, and we'll draw a little x-axis here. And we're not going to have any j components, but I'll just use I to indicate that this is in the x direction. Okay, let V2 be double that, 80 centimeters per second. And after I write I, if I change something, I want to write j, because I'm not thinking. I get in a lot of trouble for things like that. And you can't quite see what's up there at the top of the board, so let me fix this. Okay, good. So we've got V1 and V2. M1 is 70 grams. M2, we'll let this be just 40 grams. And then let the velocity of the second ball after collision be 20 centimeters per second. Now I'm being nice to you, nice to both of us, because I could say, okay, we don't know what U2 is, but we know that after collision from this point, this thing falls 1 meter with a horizontal range of 20 centimeters. Well, that's enough information to analyze the projectile and determine what the velocity of this was after collision. So we could do that sort of thing and watch it, because that's the sort of thing I'll sometimes put on an exam or something. We mix things. But, you know, we'll see how that works. Okay, anyhow, so let's just say one way or another you determine that U2 is 20 centimeters per second. Experimentally, what I just said, seeing how far this thing then travels before it hits the floor, is not a bad way to measure U2. You have to be careful that collision's really head-on, though. Well, there we have all the information we want. And now we can answer any question we want, like how far is this thing going to swing back? Okay, but for the moment, we have enough information to analyze the collision, so let's just do that, and then we'll worry about swinging back. And of course, as it swings back, this tension is going to become important, and the whole theory of simple harmonic motion of a pendulum becomes important. Okay, so we got all this, and we can then easily calculate using this, we can solve for U1. And actually, the equation's the same as the one we used before, except I don't have to have arrows over these V's because everything's in the I direction. M1 V1 plus M2 V2 minus M2 U2 all divided by M1. Now, I think I had M1 U1 here and M2 down here last time, but it's a similar type of thing. And if we want to continue, if we want to write this as a vector equation, all of these vectors are times I, so we can do this. And now we've got U1 is going to be a multiple of I. But we can it's not really necessary to do that, but I'm going to do it anyway. Okay, so now we just calculate this, and I'm not going to write out the details. I'm just going to multiply these. I know the units are going to work out, and how they're going to work out. We just saw that, so I'm just going to put a couple of dots here. Well, yeah, you really want to write that out. You really want to work it out, but let's just do this because the numbers are simple. Well, they're not that simple because they're double digit, but they're nice and round, so it's not a problem. Okay, so M1 V1 is going to be 70 grams times negative 40 centimeters per second, which is negative 2,800 grams centimeters per second. So we've got a negative 2,800 here, and it's in the right units. M2 V2 is 3,200 grams centimeters per second. So 2,800, negative 2,800, 3,200 gives us 400 grams centimeters per second. We ought to keep reminding ourselves of the units. And then M2 U2 is M2 U2 800. That'll be minus, so we're going to get negative 400 grams centimeters per second divided by M1, and I think now I was hoping that would be, if it had been M2, I'd have had a nice round number there. Where G here is grams, could have changed everything to kilograms, and the numbers would have been decimals and stuff. But 70 goes into 400, about 59 times. Negative, 5.9 times. Negative 5.7 times, I don't know where I got that 9, but as soon as I compared that with 7 into 420, well, don't worry about it. Okay, we have this. So this thing's going to get slowed down by the collision. Now, I don't think I've specified x. So I'll go ahead and specify x here. Let's say x equals 10 centimeters and L equals, we'll just do 100 centimeters to make the numbers easy. So now what we have a pendulum of length 100 centimeters with velocity negative 5.7 centimeters per second. And since I'm doing vectors, x is going to be negative 10 centimeters because we're on the negative side if this is a positive direction. So I'll just throw a negative sign in there. And now how do we analyze the energy, the amplitude, the motion? How do we analyze this pendulum? Well, I mentioned energy. But incidentally, energy reminds me that I ran into about 3 really excellent videos related to engineering and also to art. And one to agriculture, and I emailed those to you, and I'm sure I included you in the email, but if you did get the email, let me know. I wouldn't, one of them's only about 4.5 minutes, the other 2 are 10 minutes, but till you get through finals and everything, probably don't want to waste your time on it, but put that off to the side and take a look at those. Actually, the first one, I think it's the first one. The first of the 2 10-minute videos would be worth taking a look at and thinking about the things that we've done in this course. So that's all I'm going to say about it. Not required, I'm not going to test you on it or anything. But it's 10 minutes and you would probably enjoy it. And you'd also see a lot of physics that would maybe help you pull things into a little more perspective. It's about a guy that does kinetic art, but he's got a physics background, and he's really doing some neat engineering of these things. Okay, and he talks about how he approaches it. And just seeing the things move, you're going to think about angular motion, you're going to think about linear motion, harmonic motion, all kinds of stuff. Okay, back to this. We've got a pendulum of length 100 centimeters with this velocity at this position. What's that tell us? Well, I actually also want the mass. So let's put the mass in here. Its mass is, what did I say, 70 grams. And now we have everything we need to nail the simple harmonic motion, even including phase angles and stuff. Not sure I'll go to phase angles. I don't want to run you off right now, but yeah, I might well do it because it's something you kind of need to know. Okay, so do we have a look, we've got this pendulum. What can you tell me about the pendulum? Do the energy analysis. Potential energy is 1/2 kx squared, where k now this g is not grams, that's gravitational acceleration. So we have k equals 0.07 kilograms times 9.8 meters per second divided by 1 meter, which is going to approximately equal 0.7 newtons per meter. That means per meter of pullback you get 0.7 newtons. So if you go 1/10 of a meter, you're going to get 0.07 newtons. So, you know, right away then, we know how much force is being exerted here by the tension in this string. How much force is being exerted in the approximately horizontal direction on this pendulum. Okay, so we can easily calculate that, but more importantly, we can calculate the potential energy of this pendulum. Now, since we can calculate the force on it, we know the mass, we can also calculate its acceleration, all kinds of things. Now, the one thing you don't want to do in our final assignment, which is on simple harmonic motion, is you do not want to use the equations of uniformly accelerated motion, something I've been pleading with people not to do all semester, because people want to do that. I don't like to see that on final exams. It depresses me. Okay? Right around Christmas time, you don't want to have that on your conscience, so don't do that, okay? Seriously, for the sake of your understanding and the ding you would get on your grade, which would be a fairly substantial ding for that kind of mistake, don't do it. And don't worry about my Christmas mood, it's always good. Okay, so, K is this. Okay, well, let's see now. We got K, we got potential energy, we got X, so we can calculate potential energy. Now, I've been going on for a while. I want to make sure the video doesn't go too long, but we're in good shape. Okay. Potential energy is 1/2 kx squared. Now, I don't know if I'm going to get these numbers right or not. You know, I'm prone to errors and carelessness mainly. But we get 1/2 of 0.7 newtons per meter times 0.1 meter quantity squared. And of course, I'll note that our negative 10 centimeters is negative 0.1 meter. And it's negative 0.1 meter squared, but since we're squaring it, the negative sign doesn't make any difference. That's going to be 0.01. Multiply that by 0.7, we get 0.007, and half of that is 0.0035. And that's Newton meters squared over meters, which is Newton meters, which is joules. Okay, there's potential energy. Okay, at this point, the pendulum has this much potential energy. What about its kinetic energy? Well, that's even easier. That's 1/2 mv squared, which is 1/2 of 0.07 kilograms times negative 0.057 meters per second quantity squared. Of course, writing the centimeter per second, the negative 5.7 centimeter per second as 0.057 meters per second. Okay, well, if I squared 0.05, I get 0.0025. If I square 0.06, I get 0.0036. So I think that's going to be about 0.0033. Okay? And if that's 0.0033, multiplying that by 0.07 is going to give us, and I say I'm going to start getting my zeros messed up. My power's a 10. I should think through this in scientific notation, but I'm way too stubborn to do that. So let's see, 0.003 times 0.1 would be 0.0003, and then that's going to be 23. Okay. I think 3 zeros. 1, 2. Joules. check my arithmetic because that was a little bit much for my feeble working memory to handle reliably. Okay, so anyhow, we have this and this, so let's just assume these are right, and if they aren't, it's real easy to correct. So now we know the total energy of the pendulum. So total energy is this plus this, and that's about 0.0036 joules. That 2 on the end there, well, it's fun estimating that, but given the approximation here, of course that wasn't really an approximation, but, you know, and given the imprecision of this calculation, I just round that to 0.0001 joules, because that 2 becomes not a significant figure in the actual calculation. Okay, well, so now what have we got? We've got a pendulum. K equals, I figured it out a minute ago, 0.01, I don't want to think that hard right now, 0.7 newtons per meter. The velocity negative 0.057 meters per second. Total energy .0036 joules. Mass is 0.07 kilograms. What's the amplitude of the motion? Well, I could just write down a formula, but let's write this down as total energy is your 1/2 kx squared plus 1/2 mv squared. When x equals a, which is the letter we're going to use for the amplitude, what's the velocity of the pendulum? Well, the amplitude's out there where the pendulum comes to rest before starting to swing back. Velocity is 0. It follows then that 1/2 Ka squared equals your total energy. Because when x equals a, b is 0. So you just have 1/2 Ka squared equals your total energy. So A is the square root of 2 times your total energy divided by K. And now we're going to see if my arithmetic made any mistake. Now that's going to then be, okay, well, your total energy is 0.0036 joules. Multiply that by 2, you're going to get 0.0072 joules. and you're going to divide by K, which is 0.07 newtons per meter. And that's going to be the square root of 0.1 I think that'd be 0.13. A joule is a kilogram meter per second squared. And actually, let's just say a joule is a newton meter. Over a newton. Well, okay, let's be really a little more clear on that. Not just by removing as much of that smudge as I can. So I'm going to say it's Newton meter times the reciprocal of Newton per meter, because we're dividing by Newton per meter. And that's going to be the square root of something's messed up here. I think I don't have, I do have enough zeros on the potential energy. Yeah, something's going to be messed up. Anyhow, it'd be 0.13 meters squared. And of course, the square root of that's way bigger than what it ought to be. And that's going to be like 0.3637 meters. And that's not a good amplitude, because when the pendulum is only 1/10 of a meter from equilibrium, okay, this is easy to correct. I just did a bonehead thing. This is 0.013. And the square root of 0.013 is about 0.11. I don't want to interpolate that. 0.117 meter, approximately. Okay, check me on that. Okay.